Alright, hell yeah. So we have an awesome statics problem. This was sent in by a German student. And this is really cool because his professor just kind of goes all out, makes kind of technical problems that are kind of interesting. Now, there's two aspects of this problem that I think I'm doing not correct towards the actual answer. One is I have no idea what this is. I'm assuming that this is just a slider. It's just wheels going across the ground, and it can only have a normal force. It can only have an upward force. It can't have a force this direction on this pivot. Now, the other aspect of this, I'm assuming that these beams are massless. Like, obviously, if they had mass, you would probably get like kind of a more normal answer. But I think here was the crux of the problem. I'm going to try to do this in under 10 minutes, one shot. Is this pin right here. I was so fascinated with analyzing it. It's so difficult to do free body diagrams on like a pin because, hey, if I push up on a pin, then it's hitting a couple other things. It's hitting this beam and that beam. So that's what we're blowing up is right here. I'm going to say we have a force on this pin. And if I push an upward force on this pin, the first thing that's going to happen is this pin is going to hit this rigid cantilever, and that cantilever ain't moving. So all the load, I'm just going to assume all the load is going to go right into the cantilever. And then I'm going to look at this member and see if that's the case. Now, one of the aspects of these problems that I think is kind of interesting is just pretend like this thing is in outer space and just kind of floating. And then you're able to still make rigid connections in outer space, and you're able to hook everything together. You're able to make this flat thing in outer space, but basically 0g. So then if you don't have a force on something, so now I'm going to analyze this little beam over here. Is this beam just floating? You know what I mean? If it had weight, it would actually be weighted down on this side. And if it did have a weight W right here, half the load would be there, half the load would be there. And so it would push against this force. So I think I am oversimplifying it, but it's fine. If these are massless, hey, right now there's going to be no force down from this member. It's just chilling. We haven't done really anything with it. And with that said, I'm ignoring this moment, just for a while. So just to show you that, hey, if I apply this upward force on this pin, it's all going into this cantilever. Okay, hell yeah. So that's what I did. And then I said, well, we still got to analyze this beam, and we do a free body diagram. We chop it out of we chop it. I like to consider it chopping it out of outer space. Another way is like I'm going to chop this beam out and have it be the only thing in the universe. And it's just floating there as well. And then I go back to Earth and be like, hey, have we put any forces or moments on it, like forces or torques? And hell yeah, we put a moment right on this corner. We're wanting to make it rotate. But we know back on Earth, visually, that this is a statics problem. There is no movement any direction or rotation. So there has to be something to counteract this rotation. And so that's where we just break out the sum of the moments at B. And so it doesn't matter what the reactions are over here. We can sum the moments at any point we want. And we're going to sum the moments right there. We're still going to have this force, Fa, or this moment, Fa. And we got to counteract that. The only place we can counteract it is over there. This distance is A. So this force would generate a moment in the other direction of Fa. So now this is balanced. But we added a force. And what we know is if we just have a mass sitting there in outer space and we add a force to it, it's going to be traveling across the universe that way. We know that's not the case. We have to balance that force. The place to balance it was back at B. We summed the moments. It didn't matter what the reactions were at B, but once we find this force, hell yeah, that reaction at B has to be downward. And so that's what we have going on right there. Oh, yeah, so I get it. I get how maybe this isn't a, maybe this drawing, so maybe I am right, but maybe this drawing isn't rollers, but it's a frictionless surface, but it's a frictionless surface that can't move vertical. I don't know, because we do have an upward force on this member. Or a downward force? Oh no, we have sorry, I apologize. No, we have a downward force on that member. I don't know what the hell I was even thinking. Okay, so that's going to be our reactions over there, and so now we have this idea that this member, due to this force, and this is kind of where I bring in the ruler, is putting a moment on this, and if it's a dynamics problem and we put this torque, it's just going to move until something stops it from moving, and that's going to be this force right there. So that's going to be that, and this moment is going to equal to this force times that distance. But we need something to stop this moment and to make sure that this thing isn't moving, and we need this applied force right there. So when we analyzed this force on this pin and we said it was just operating on this cantilever, and we said, hey, this member minus this moment was just floating, so we analyzed, we got up to that part. But then we said, oh, this member does have a moment on it, and it's pushing down with a force F. So I can say, hey, it's the same thing as someone pushing down with their hand right here, a force F. Well, that's pushing against the pin. This pin is pushing up against the cantilever. This is pushing the pin down with force F. So then this is the picture you're going to see. Like, hey, yes, you're going to have a connection here of a force F. This force up is going to push against this member. But now this is just going to be floating in this cantilever. So there's going to be no force in the cantilever. Now this is for the problem where these rods are massless. If these beams aren't massless, well then you're going to have a variance. And but just from there I was just like, okay, hell yeah, there is no force in the cantilever. Now we can move on. And can I do this in 3 minutes? Okay, so then we probably not. I'll probably do this in a couple videos. But that, so I'm gonna end it there, because that was how I deduced that this member had 0 forces. So this is going to be part 1. This member had 0 forces on it, and this member had these forces. It had that moment, a force up, and a force down. But I think that's an oversimplification, because I think the teacher wanted them to assume that these had mass. This would be, 2W, and then this would be W over here. I don't know, but I'm just going to consider they're massless. But I still could have made an assumption that made an error here. But anyway, so that was part 1. And yeah, it took me I don't know. I do 3 or 4 or 5 hour videos. But hell yeah, I thought that was the key point. Really looking at this pin, because I wanted to analyze. Pins are the hardest thing to do free body diagrams on and analyze, because you got like 3 things, connected and touching all at once sometimes. Okay, so hell yeah, that was part 1. Part 2 is going to go over the reaction forces. You know what I mean? It's going to be the bending moment sign conventions. That's going to be part 2.